Assalamualaikum. So today I'm going to talk about this electrogravimetry. Okay. So at the end of this topic, you should be able to describe the principle of electrogravimetry and its application for quantitative analysis of analytes. Okay, look at this. Okay, again, I've shown you several times about this flow chart. Okay, so this electrogravimetry located at the bottom of the flowchart. Okay, it come under two different side here. So one is under V constant. Okay, another one is I constant. Okay, these dynamic methods and the interfacial methods. Okay, we talk about this electrogravimetry. So electrogravimetry analysis is more or less similar to conventional gravimetric analysis. Okay, so this is a chemical reaction. Okay, you just mix for example A and B. Okay, reactants A and B, then they will react chemically, okay, through chemical reaction, and it forms solid products. Okay, then the precipitate or solid product will be heated and undergo the drying process. So then you put in the oven and then you will weigh it. Okay, so you know how much mass, okay, collected on the filter paper. However, in electrogravimetry, okay, the product is deposited quantitatively on an electrode by an electrochemical reaction. Okay, either using current or potential, and the amount of the product formed will be determined by weighing the electrode before and after electrolysis. Okay, so for example, in this case, okay, so you have this, the coil, okay, this is the working electrode. So this the case of platinum goes as cathode or the counter electrode. So this is the reference electrode, should be included in here. Okay, reference. Okay, so what is your target is the working electrode, the substrate. Okay, so the electrochemical reaction will undergo at this working electrode. So the deposition of product will be formed on the working electrode. So either by applying ampere, okay, constant potential current or constant current. Okay, so we must measure the working electrode before do the electrolysis or electrode deposition and after the electrolysis. So you will know how much mass. Here you can use this formula or equation Q. Okay, you are measuring, actually it's similar to colorimetry, but it involves additional process, which is weighing process before and after the electrolysis. So the formula is similar to colorimetry, but it involves the measurement of mass deposited on the electrode. Okay, so this is M refer for moles. So moles is mass over atomic mass or molar mass. Okay, so you can calculate, you will know the mass produced or deposited on the electrode, then you can find the moles reacted from the electrolysis. Okay, so it also for this electrogravimetry involve the Faraday's first law as well as Faraday's second law. Okay, according to first law, the mass of substance liberated, okay, liberated if they are gases, or deposited if they are solid at the electrode during electrolysis is directly proportional to the quantity of electrical charge or Q, okay, that pass through the electrolyte during the electrolysis. So you can use this. Okay, so this is the relation between mass and the charge pass. Okay, for second law of Faraday's, okay, the mass of different substances evolve, liberated or deposited by the passage of same quantity of electricity are proportional to their chemical equivalents. So these are the chemical equivalents. So M1, small letter M1 is the uh, okay, M1, M2 are the mass. Okay, M1, M2, okay, two different substances. Okay, so M, capital letter M, and M, capital letter M2 are the molar masses for 1 and 2, substance 1 and substance 2, and N1 and N2 are the valence number or oxidation number for uh, element 1 and element 2. Okay, so you should relate the 1 and 2. So they should have the same ratio between 1 and 2 if you use the same quantity of Q, electricity, for the deposition. So electrolytic precipitation or electrodeposition has been widely used for the determination of metals. Okay, in most applications, the metal is deposited on a weight. Okay, this is the substrate, platinum. So you must weigh the platinum or the working electrode before doing the experiment and reweigh the platinum again with the products. So then you can calculate the mass. Okay, with after, and you deduct with the before for this platinum cathode, for example. So there are two types of electrogravimetry methods. One is constant current, by using constant current. So we call it chronopotentiometry. So you just measure potential V with time. Chrono is time. Okay, so you can plot V versus time. Okay, then you can also when you measure V, you must use I constant. Okay, so if you plot I current versus time, you should plot this, a constant current, okay, flowing during the process, but V potential will increase. Okay, so for the second type, which you use constant potential, okay, we can call it chronoamperometry. What are you measuring for this constant potential is the ampere current with time. Okay, you are measuring current with time. So you can plot I versus T, so you will get this shape because the current will vary with time. Okay, so gradually it will completely reduce or oxidize or reduce on the working electrode. Okay, look at the first one, constant current, or amperostatic or galvanostatic. So electrode deposition will be carried out by keeping the current constant. Here, periodic increases in the applied potential are required. So by adjusting the potential of the cell as the electrolysis proceed. Okay, so this you just apply a constant current here. Okay, this technique we call it chronopotentiometry. You can measure the increase of voltage potential with time. Okay, so for the constant current, okay, so you expecting to produce metal deposit which produce or coated on the substrate, okay, for example platinum, to produce a very pure metals deposited on the substrate, and the deposit must be strongly adhered, okay, to the substrate, very dense product or deposit, and very smooth. Okay, so it can be washed and dried and weighed without any loss. Okay, product loss. So if okay the product is spongy, powdery, or flaky, okay, the contradict to this the first product deposit. Okay, if you get it spongy, powdery, or flaky deposit, your product or the metals are likely to be less pure. Okay, a lot of impurities, and it also will be less adherent. Okay, it poorly adhered to the substrate. Okay, so I'm talking about the product. So for example, this is platinum. Okay, so for example, silver will approach the surface of this is cathode, so it will reduce by accepting one electron. So it will form a layer of film, silver film on the platinum substrate. So if you produce a very smooth film of silver, the most likely it will very pure, 100% silver metal formed on the platinum. And the coating of silver is very strongly adhered to the platinum surface, the cathode. And the morphology is very dense and smooth. But if you get silver deposit which is spongy, powdery or flaky, so it could be less pure and less adherent to the platinum. It can easily remove from the platinum substrate. Okay, the principal factors that can influence the physical characteristic of deposit are current density, temperature, this is current or current density, I, small letter I, temperature, and also the presence of additive, for example, complexing agent. All these factors can influence the formation of deposit or the coating. So simultaneous evolution of gas at an electrode, okay, simultaneous evolution, okay. For example, silver, okay, will reduce to silver metals. Okay, at the same time, there is a competing reaction with the hydrogen. If you use acid as the electrolyte, so simultaneous evolution of gas. Hydrogen gas also will be formed at the platinum. So there are competing reaction. Okay, so your target is to produce silver metal, but at the same time, hydrogen also wants to reduce on the platinum surface. So during deposition is not a desirable factor, since continuous evolution of bubble on the electrode surface will disturb the orderly growth of the crystal structure of the metal deposit. Okay, so the evolution of hydrogen, for example, during the deposition of silver will lead to will interfere in the formation of very good structure of silver. Okay, so it will disturb the growth of silver on the platinum. So as the result, porous and spongy deposit, for example, silver will be obtained, okay, if there are continuous evolution of hydrogen gases on the platinum surface or substrate. Okay, next, potential changes during an electrolysis. Okay, we are going to talk about potential, E or V, voltage changes during an electrolysis. We are still talking about I constant. You are applying constant current. Okay, so you will plot, if you plot I versus time, so you will get a straight or constant current with time. But if you want to look what happened to voltage, if you use constant current, so it will change. It's not constant. V is not constant for I constant. Okay, so if you use this technique, I constant, you will see I is constantly flowing during the deposition. But V, the potential is not constant. It will increase. Okay, because this technique is current constant, using constant current. Okay, consider electrolysis of copper to plus, okay, in acid medium at constant applied current. Okay, at constant stirring at 50 degrees Celsius. Okay, so what are you trying to do is electrolysis of this element. Okay, copper to plus. Okay, in acid medium. Okay, H plus. Okay, using a constant current, I constant. So a weight platinum cathode. Okay, weight. You must weigh this platinum before doing this electrolysis. Okay, so then the anode also is platinum wire. Okay, cathode is platinum. Then the anode also platinum. So this is platinum. So this is platinum. So let's say this is voltage, okay, or current, constant current, and voltage. So in this solution, it contains copper and also acid, okay, beside water. Okay, so this is cathode, this is anode, okay, platinum. Okay, so the electrochemical reaction during the electrolysis at anode here, okay, is the evolution of oxygen gases. Okay, oxidation, water will oxidize to form oxygen gas. A lot of bubble will form at the surface of platinum anode. Okay, at cathode also platinum. Okay, so the reduction of copper. Okay, copper will reduce to form copper deposit. Okay, we call it deposition of copper at cathode. Okay, beside that, hydrogen also try to evolve at cathode. Okay, but since this reaction is easier than hydrogen evolution, so the reaction at cathode will be dominated by this process. So this is the overall reaction. Okay, you combine these two, you will get overall reaction. Okay, so copper will reduce to copper metal, water will oxidize to form oxygen. The applied voltage rises significantly. Okay, the voltage will rise significantly at the end of the electrolysis due to the evolution of hydrogen gas. Okay, so this is lower voltage is the copper reduction, copper 2 to copper 0, but slowly the amount of copper will decrease since a lot of copper will deposit here. Okay, the amount of copper 2 metals in solution will decrease with time. Okay, so then what ion will be dominant in this solution at the end of the electrolysis is the hydrogen. So once copper 2 reduce, this one will take over the process. Okay, the hydrogen evolution. Okay, so that's why this hydrogen voltage will increase with time. So co-deposition of hydrogen during electrolysis often leads to spongy and flaky deposit that do not adhere to the electrode. It do not strongly adhere to the electrode. Okay, so if you use constant potential current, so the problem is at the end, if you do the electrolysis or electrodeposition at longer time, a very long time, so you will tend to form the top surface of the product is spongy and flaky due to co-deposition. Okay, co-deposition between copper to copper and also hydrogen to hydrogen gas. Okay, so the first, for example, this is the platinum. So that earlier deposit was very strongly adhered, which is copper, but slowly it become porous because hydrogen gas also evolve on the surface. Okay, so this is copper, but it's spongy and flaky. But the underlayer of copper film is very strongly adhered to the platinum, to the cathode. But the top layer probably will produce a spongy and flaky, easily remove the top layer. But under layer is very strong because there is no interference from the hydrogen evolution at the beginning of the deposition. Okay, so the voltage will increase due to concentration of copper will reduce with time because a lot of copper 2 plus ion will form deposit, copper deposit, and hydrogen will dominate the process. Okay, this the typical application of constant current electrolysis. Okay, you can see this. So the analytes in the solution, in the test solution, is silver ion. So you are going to deposit silver on platinum. Okay, so this is the substrate, cathode. So silver plus will reduce to form silver metal on the platinum surface. Okay, for cadmium, okay, so cadmium 2 will reduce to cadmium, okay, on the copper. You cannot use platinum, okay, directly, so you must put copper on the platinum surface, because if you use platinum, hydrogen will be easily evolved, because hydrogen, if you check the standard reduction potential, hydrogen on platinum is 0 volt. Cadmium is more negative value. Okay, I'm not cannot remember, 0.5 for example. Okay, more negative. So more positive is easier to be reduced. Okay, on cathode. Okay, so since this metal cation is uh, uh, is more difficult to be reduced on platinum, that's why you must use copper. Okay, you get platinum and coat with copper. Okay, copper coated on platinum. So the outer surface is copper, not platinum. You cannot use platinum, okay, directly, because hydrogen will evolve. Okay, so then copper. Copper, since copper 2 plus is more positive, 0.34, so it's no problem if you use platinum substrate, okay, for the deposition of copper. So at the anode, okay, you should use this. This is the oxidation. Mn2 plus, okay, will oxidize to MnO2. Okay, 2 minus. So this is in the form of Mn4 plus. It oxidized from 2 to 4. But in the form of manganese dioxide. It occurs on the anode surface, not cathode, because it is oxidation. Okay, so for nickel 2 reduced to nickel 0, it should be done on copper, not platinum. Okay, so again, you should coat copper on platinum. Okay, the same reason which hydrogen is easily formed, hydrogen gas easily formed on platinum. So nickel is located lower, okay, in the series. So hydrogen is easier to be evolved on platinum. That's why you must use copper, which has large potential for hydrogen evolution. Next, platinum, lead. Lead 2 plus will oxidize to lead dioxide. Okay, so Pb2 plus to the form of Pb4 plus, but in the form of metal oxide. So it can be done on platinum anode. Okay, zinc 2 plus reduced to zinc 0 metals. You should use copper instead of platinum. Okay, so the same reason, the hydrogen evolution. Okay, so bromide. Okay, so you can form silver bromide. This is on anode because it oxidizes. -1 to 0. Okay, so this is on silver. Bromide will deposit on silver. Okay, so this is about constant current. Okay, next is V constant or potential static. V constant. You just set the potential at constant value of potential. It is possible to separate two elements whose deposition potential differs sufficiently by using this method. Okay, you can separate, for example, copper and zinc. Okay, if in your solution contain these two metal cation, so you can separate the two elements using this V constant, because each of these elements has different deposition potential. Okay, for example, is standard 0.34. This is 0.76. So it's very wide separation. So you can easily reduce this first, because this is more easily reduced. This is less easily reduced. Okay, you can separate the two ion. Okay, in the mixture, in the solution contains Cu2 plus and zinc 2 plus. So you can separate this by using this technique, potential static. Okay, you set this potential first, then let all the copper reduce to copper 0 on the platinum, then followed with this. Then you set a new voltage, V constant. V constant 1 at this and V constant 2 at this. So you can separate the two elements using this V constant because both have different deposition potential. Okay, successive deposition of metals. Okay, so you the same case, a mixture of copper, bismuth, lead, cadmium, zinc, tin. There are 6 elements. Okay, in the container. So you can do a successive deposition of metals. Okay, by knowing of its voltage deposition potential for each of these elements. Okay, first copper will be deposited, okay, because it's the most easily or readily to be reduced or reduced element. Okay, then you can weigh the cathode. So cathode is platinum, so you can deposit copper first, so it will form copper metals, okay, on the platinum. So then you weigh the platinum with copper, then you know the mass of copper deposited on the platinum cathode. Then now the material is new substrate, copper deposited on platinum. So now you can deposit bismuth. Okay, bismuth can be reduced on copper, not platinum, because the first step, copper is already formed on the platinum substrate. So now the new surface is copper, not platinum, but copper coated on platinum. So bismuth is the second element easily reduced. Okay, then followed with lead. Okay, be lead 2 plus. Okay, can be deposited on the same electrode. Okay, next, all these 3 elements, copper, bismuth, as well as lead, okay, are deposited from a neutral solution. Okay, which form complex with tin. Okay, it's very complicated or complex reaction. Okay, so but what I like to tell you that you can do a successive deposition of elements or metal cation on the using this constant potential. Okay, at the end you will do the deposition of cadmium in different environment. Okay, in the chemical environment. Okay, so and also zinc. Okay, finally, so you will identify tin, stannum. Okay, 2 plus, you will deposit at different voltage. Okay, so it's very complicated, but what you should know is you can do successive deposition of many or various cation present in the deposition or buff solution. Okay, so by knowing their voltage or deposition potential. Alright, then also you can do this simultaneous deposition. A mixture, for example, a mixture of copper. Okay, copper is a mixture solution of copper and lead. Okay, can be determined. Okay, you can determine what is the concentration of copper and what is the concentration of lead by doing the simultaneous deposition. Okay, for example, in this container contains Cu2 plus and lead 2 plus. Okay, at anode, this is anode and this is cathode. Okay, so by applying constant potential, so copper will reduce here. Okay, copper will reduce to copper on the platinum. Lead will oxidize to lead 2. Okay, Pb will oxidize to PbO2. It's a solid. Okay, solid material, lead dioxide. Then you can do the weighing process. Okay, weigh the before electrolysis and after the electrolysis. So you will know the mass of copper deposited here, as well as mass of copper dioxide formed here. Then you will do the calculation. You will know how much Cu2 plus and Pb2 plus present in the test solution. That's all. Thank you.